Hey there again, geometry students. Today we're going to be covering section 9.5, the sine and cosine ratios. These are a couple more of the trig ratios. They're going to be building off that tangent ratio that we covered in the last video. So to begin, what are sine and cosine? So like I said, there's some trig ratios, and they're going to be looking at the same acute angle as the tangent ratio, but the proportion that's on the other side of that equal sign is going to be a little bit different. So we have our right triangle. Let's just call this vertex A, B, and C. So our sine ratio, and we shorten sine to just SIN. So let's look at sine of angle A. So we're going to be looking at this one. Sine of angle A says we're going to be looking at one of the lengths of the sides here over another length. And sine is the opposite side of angle A, which is this one here, over the hypotenuse. So the opposite side length of angle A over the length of the hypotenuse. And that's our sine trig ratio. The cosine ratio, which we're going to abbreviate COS, and we'll look at angle A also. This one's set up to be the adjacent side. So if we're looking at angle A, BC is opposite of it, and AC is adjacent to angle A. So really the length of the leg adjacent to angle A, and this is all going to be over the length of the hypotenuse as well. And these are just two more trig ratios. And we have one more vocabulary word, which is angle of depression. And this is an angle that a line of sight going downward from a horizontal line. So here's our horizontal line. Our line of sight goes down here. This is our angle of depression because it goes down, similar to that angle of elevation, which goes up from that horizontal line. So now that we have our vocabulary words and we've set up our two other trig ratios, the sine and cosine ratios, we're ready to move on. There's another interesting fact about the sine and cosine ratios. So we're going to be looking at complementary angles. Do we remember what those mean? So complementary angles are two angles that add up to 90 degrees. So in our right triangle, we have our 90-degree angle here. So the other two have to add up to 90 so we can get our 180 degrees in our triangle. So we're going to be looking at these two acute angles. And let's just go find the sine of A. So remember, it's the opposite of A over the hypotenuse. So here's our angle A. The opposite side is 4. And it's going to be over the length of the hypotenuse of 5. Now just for fun, let's look at the cosine of, say, angle B. We're going to be looking at this one here now. So the adjacent side to angle B is this 4, and our hypotenuse is still 5. Well, that's interesting. So the sine of A is equal to the cosine of B. That's because the sine of an angle is equal to the cosine of its complementary angle. So let's put this in math form. Sine of A equals the cosine of 90 minus A. And this makes sense because we have 90 degrees here and we have angle A. So 180 minus 90, which is this one, minus A, we're left with the measure of angle B. So we're going to do that cosine of B. And this is the same for the cosine. So the cosine of A, and it'll be equal to the sine of 90 minus A, which is just B. So sine of A equals cosine of B, and cosine of A equals sine of B. I love when this math stuff, it just looks so pretty sometimes. So we just finished our mini lesson about sine and cosine ratios. Now let's begin the homework. So we have 3, 6, 9, 12, 15, 18, 21, 23, 24, and 27 from section 9.5. The instructions for number 3 and 6, they're telling us to find sine of angle D, sine of angle E, cosine of D, and cosine of E. And just like in section 9.4 with the tangent ratio, they want us to write in fraction form. And then also as a decimal to 4 places. So let's begin. We got number 3. We always want to draw out our triangles. Helps us visualize the information. So we have a right angle up here. D, E, F. And they give us side lengths of 12, 15, and 9. All right, so let's just start with sine of D. So here's our angle D here. So if we're looking at the opposite side, we need opposite over the hypotenuse. So we look all the way across, we got 12. And then our hypotenuse, well, here's our right angle. So it's the side opposite the right angle, 15. So sine of D is 12 over 15. Can we simplify that fraction? I think we can. We divide it by 3. So let's divide the top and the bottom by 3 and we get 4/5. So there's our fraction form. Now they want us to write it in decimal form to 4 places. That's simple enough. We'll just do 4 divided by 5. And we don't even need to go to 4 places because we'll just get 0.8. So there's our 2 forms, the fraction and the decimal, of sine of D. Now let's look at sine of E. So here's our sine of E right here. And again, the sine ratio is opposite over the hypotenuse. So for angle E, our opposite side is 9, and our hypotenuse is still 15. I think we can simplify this one too. And dividing by 3 looks like a good idea. So this time we get 3/5. Now in decimal form, we just divide 3 by 5. And we get 0.6. All right, so there's our 2 sine ratios for this triangle DEF. What's left now is to find the cosines. So let's start with cosine of D. So we're back to angle D. And cosine is adjacent over the hypotenuse. So we're looking at this adjacent side over the hypotenuse. Oh, 9 over 15. We already got this. And that's not surprising because that last thing we just looked at was the sine and cosine of complementary angles. And sine of E is equal to the cosine of its complementary angle, which is D. So sine E equals cosine D. Do we need to find cosine of E, or can we just look up here at sine D? I think we could just look at that sine D. We're going to use our properties to know that sine D equals the cosine of its complementary angle. So we can just go cosine E is the complement of angle D. So we already know that this is 4/5 and 0.8. So it's not like a lot of work, but if we can remember these properties that they give us, the complementary angles, we really only need to find two, because then we know the cosine of the complementary of sine E is the same. So we really don't have to do half this work, which always sounds good to me. All right, so let's go to problem 6 now. It's asking us to do the same thing we just did in this last problem. Just find the sine of D, sine of E, cosine of D, and cosine of E. So I have that triangle written down. I want to draw it correctly for you guys. So there's our triangle D, E, F. They give us side lengths of 27, 36, and 45. So let's dive right in. Sine of D. So we're looking at this angle up here. Which is the opposite side of angle D? That's right, it's going to be 36. And then over the hypotenuse, here's our 90 degree. And the side opposite of that 90-degree angle is 45. All right, so we're left with 36 over 45. I think we can simplify this one also. This one goes down too. What are we going to divide both of them by? I think 9 works. 9 goes into 45 5 times. 9 goes into 36 4 times. All right, so we got 4/5. We already know the decimal for that one because that's just like the last problem. So there's our fraction and our decimal form. Now let's do sine of angle E. So we're looking at this angle here. Opposite side over the adjacent side. All right, so we know 9 goes into 45. Does 9 go into 27? Sure does. So we got 3 over 5. That's just like the last problem too. So we know that decimal is 0.6. All right, let's go on again. Let's look at the cosine of D. Back up here to angle D. So look at the cosine now, which, as we remember, cosine of D equals the length of the adjacent side over the hypotenuse. So it's 27 over 45. Oh, and again, that's the same as sine of E, because D and E are complementary angles. So the sine of E is equal to the cosine of its complementary angle. And do we have to work out cosine of E? Or do we already know what it's going to be? We already know what it's going to be. Sine of D is equal to the cosine of its complementary angle. Complementary of angle D is E. So sine of D is equal to the cosine of its complementary angle E. So we can just go 4/5 and 0.8. I love when this math comes together to make things simpler. So we don't have to work out every little thing as long as we recognize the rules they give us, that sine of d is equal to the cosine of its complementary angle, which in this case is e. Sine of e is equal to the cosine of its complementary angle d. And these go both ways. So I could say, if we found cosine first, cosine of d, we already know that the cosine of d is equal to the sine of its complementary angle, which is e. So they work both directions. We don't just have to start with sine. We could have started with cosine of d and cosine of e and easily found these sine ratios. All right. So our next problems, we have some different instructions. It's telling us in 9 and 12, write the expression in terms of cosine. In terms of cosine. All right. So they give us, for number 9, the sine of 37 degrees. So what we have been using the last couple problems, which is complementary angles, we're going to be using this in this problem as well. So let's just set up like the general expression. Sine of A equals cosine 90 degrees minus A, and cosine of A equals sine of 90 degrees minus A. All right, so we're given sine of 37 degrees. Let's just add this right onto the back end. Equals cosine of 90 degrees minus A. So we got cosine of 90 degrees. And A is an A. So we got 37 degrees here. So we're going to subtract 37 degrees here. Now we'll do a little bit of math on this side. And we have 90 minus 37. Cosine of 53 degrees. So this is the property sine and cosine of complementary angles. We're going to be using this in number 12 also. So number 12, they give us sine of 64 degrees. And again, they want us to write this in terms of cosine. So we use this same one here. And I'm just going to write on the back end of this. So we have sine of 64 degrees equals cosine of 90 degrees minus 64 degrees. We do a little bit of math here. And we get cosine 90 minus 64, 26 degrees. It's pretty straightforward, just using the properties that we know to rewrite this sine of 37 as the cosine of its complementary angle, 53 degrees. And sine of 64 is equal to cosine of 26. Let's draw a picture just to check to make sure this all works. We have 90 degrees here. Let's just look at number 9. So it's 37 degrees here. We know 90 minus 37 is 53. So let's just go ahead and fill in this here. So we're looking at the sine of 37 degrees. It's opposite over hypotenuse. So we're going to be looking at that value here. And let's just call the hypotenuse h. So sine of 37 is x over h. Now let's look at the cosine of 53 degrees. Cosine is adjacent over hypotenuse. So this length here, which is x over h. So, yep, we just checked our answer to make sure it makes sense, and sure enough, it does. It's always a good thing when that works. All right, so we're moving on to number 15 now. Similar to the last one, but now we're going to write the expression in terms of sine. So they give us cosine of 73 degrees, and they want us to write this in terms of sine. So we're going to use that same property. Sine of A equals the cosine of its complementary angle, or the cosine of A equals the sine of its complementary angle. So we have cosine 73, so we're going to be looking at the sine of 90 degrees minus 73 degrees. We find this number to be 17 degrees. So cosine of 73 degrees is equal to sine of 17 degrees. And this is in terms of sine now. I like it. Pretty good so far. We're just moving along. So we've just been using these sine to cosine ratios when we have all the side lengths. Now in 18 and 21, we're going to try to find the length of a side using the degrees and the other information we're given. So for 18 and 21, find the value of the variable using sine and cosine. Since we're finding side lengths, they want us to round to the nearest tenth. All right, sounds simple enough. We got this. So for number 18, let's draw their triangle. Right angle there. So they want us to find the value of variable Q and P. And the hypotenuse length is 34. And this degree, this angle here is 64 degrees. I'm just going to write that on the outside so I can write it a little bigger. Okay. Where to start out? Do we want to start with sine or cosine? I'm going to start with sine the other time. Let's start with cosine. All right, so cosine of 64 degrees equals, is it adjacent or opposite? Cosine is adjacent over the hypotenuse. We're looking at Q, because this side length here is adjacent, touches this 64 degree angle, over 34. Now we just got to solve for Q, a little bit of algebra. So we'll multiply both sides by 34. On this side it cancels out. And on this side we have 34 times the cosine of 64 degrees. We're going to need a calculator for this one. So let's get our calculators handy. Got mine right here. So we'll just do 34 times cosine. And on your calculator, it's just going to say COS. And that's the one you use for the cosine. And sine just says SIN. So when we get that, we have Q equals 14.90461. And that decimal keeps going. This isn't our answer though. in our instructions, it tells us to round to the nearest tenth. So we got our decimal, we got tens, hundreds, thousands. We're just looking at this tens. So we look at the one right next to it. If it's 5 or above, we got to round this number up. If it's 4 below, this number stays the same. Since we're approximating it, Q is about 14.9. So these problems are similar to the tangent ratio that we did last Thursday. We got that down really well. I think this should be pretty good for us. Pretty straightforward. So now we got number 18. Let's go look at 21 now. Same instructions. Oh. I didn't find the other variable. Good catch, guys. I know you saw it. I didn't catch it yet. All right, so we found the length of Q. Now we just got to find the length of P. So we're still going to be using this 64 degrees right here. So let's look at sine of 64. That's how we're going to find this opposite length. So sine of 64 equals the opposite side over the hypotenuse, so it's P over 34. Similar to the last one, multiply both sides by 34 to get P by itself. And then we get P equals 34 times sine of 64 degrees. Got to do our calculator again. Get another large, long decimal. And it's what, 30.558,997. And that just keeps going on. Okay, we got to round it to the nearest 10. Here's our 10 spot, so we look at the one to the right. And it's 5 or above. And this is an approximation now. P is about 30.6. And Q is about 14.9. So does this answer make sense? We got 30.6 down here and 14.9 there. So the 64 degrees, it opens pretty wide. 64 is a pretty big angle. So we would expect this length here to be longer than this one. This angle here is only going to be 26 degrees, so that opens a lot less. So that side opposite is going to be shorter. So our answer makes sense. It's always a good thing to check to see if your answer is reasonable. All right, so now we finish number 18. I won't make that mistake again on 21. 21, we got these same instructions. Find the value of the variable of this triangle. Got 10 on this side, B up top, and A is the hypotenuse this time. And then this angle measure is 48 degrees. All right. So say, I'm going to start off with sine. Let's try sine of 48. And sine ratio is the opposite over the hypotenuse. So we have B over A. Uh-oh. That's a problem. We got two unknowns in one equation, so we can't find out what either of these values are. Is there any other way we can find out what A and B are? We're going to use this 48 degrees. We know one value, cosine. We got cosine. Let's look at cosine 48 degrees. All right. So we have cosine is the adjacent over the hypotenuse. So 10 over A. All right, that looks way better. We only have one variable now in our equation, so we can solve for that one. Multiply both sides by A. We want A on top. Now we want to get it by itself. So we'll divide both sides by cosine of 48. And we have A equals 10 divided by cosine of 48. All right, some more calculator now. 10 divided by cosine 48 degrees. And I'm going to round it right now. It's about 14.9. All right, so that's one of our side lengths. So we're still left with a sine of 48 degrees. Is it still two unknowns now? Or did we figure out what one of them was? We got our A value. So let's just plug that in now. And that's no longer equal. That's similar to. So to get B by itself, we're just going to multiply both sides by 14.9. And we have B is about 14.9 times sine of 48. Some more calculator. Give you guys a chance to do that too. And we get, oh, these are not equal still. It's about, we have this. Just going to stop at the 100 spot, because all we're looking for is a tenth. So now we got to round to the nearest tenth. So B is about 11.1. So here's our A, and here's our B. This one was a little trickier because they made us start with the cosine one. But because we started with sine of 48, but then we got our two unknowns in the same problem. We can't do that. So then we just looked at our cosine, and that's how we found our A to plug back in here so we could find the value of B. This was a fun one. We got to use our brain a little bit. We're moving today. We are moving. All right, so our next problem is 23. And this one's asking us which ratios are equal. And they want us to, they give us sine of x, sine of z, cosine x, cosine z. And here's the triangle. Right angles up here at top. So y, x, and z. Side lengths of 3, 3, 3 root 2. Where do we start? Do we recognize anything about this triangle? Yeah, these two legs are the same. What does that mean? Does it mean it's a special right triangle? The 45, 45, 90? That it does. So now this angle is 45 degrees. This angle is 45 degrees. All right. So remember, cosine 40 of an angle is equal to the sine of its complementary angle. So it's equal to, so in this case, sine of 45 is equal to cosine of 45. And that's just because 90 minus 45 is 45. So sine of 45 equals cosine of 45. And cosine of 45 is equal to sine of 45. So we could say these are all equal to each other. Sine of x is equal to sine of z equals cosine of x and cosine of z. So in this case, in our 45, 45, 90 triangle, the sine, these ratios are all equal to each other. This angle is the same, and this is y. So we did the math to show it, and we discovered that all of these ratios are equal to each other. So if you get, there's some more properties of our 45, 45, 90 triangle. If you get one, you know that the sine and cosine of each of these angles is the same. That's fun. That is fun. All right. Let's go on to 24 now. They give us the same instructions. They want us to find which ratios are equal. We have a different triangle this time, though. So let's draw this triangle out. This is 30 degree. We know that's not drawn to scale then. But that's a 30-degree angle. Vertex L there, K, and J. 2 square root of 3, 2, and 4. So they want us to find a sine L, sine J, cos L, and cosine of J. So which of these ratios are equal? Well, it looks like we have a 30, 60, 90 degree triangle. So let's see what special properties of this triangle happens with sine and cosine. So this one, I think we're just going to have to find the sine of each of these angles and the cosine of each of these angles. Because I can't look at this right off the bat and just see. So let's actually go through it and we'll find out what we find out. See if there's anything cool about this. Sine of L is opposite over hypotenuse. Well, that's a 1. Let's try that again. 1/2. All right, now let's look at sine of J. Here's our angle J up here. Opposite over the hypotenuse. 2 square root of 3 over 4. These 2's simplify. And we get square root of 3 over 2. All right, let's look at the cosine of L now. Here's L. Our cosine is 2 rad 3 over 4. All right, we found something here. We found one that's equal. So cosine of L is equal to the sine of J. Let's see if this cosine of J is equal to this one. Cosine of J we got up here. So our adjacent side is 2 over 4. And that simplifies to 1/2. And this is kind of what we expected, because this works in every right triangle. Sine of an angle is equal to the cosine of its complementary angle. So there's nothing too fancy about the sine and cosine of these angles in 30, 60, 90. Whereas in that 45, 90, we had that the sine, this angle is equal to the sine of this angle, and the cosines were equal as well. This one just follows from our property of sine and cosine ratios of complementary angles. So these are our two ratios that are equal. All right, guess what? We are at our last problem. Problem 27. So this one, they give us a word problem. I didn't write it all down, so I'm going to read it from here. So modeling with mathematics. This is problem 27 on page 499. It says the top of the slide is 12 feet from the ground and has an angle of depression of 53 degrees. What is the length of the side? Okay. So we had our angle of depression. We saw what that was. That was one of our vocab words. And they gave us a bunch more information. Let's go ahead and draw a picture. So here's our slide. There's no steps. There's holding it up. And then this is the actual slide part. There's a little handle. It's a horrible looking slide. But that'll work for us. So they say the top of the slide is 12 feet above the ground. And there's a 53-degree angle of depression. So that's 53 degrees. Because that is our downward line of sight from this horizontal line. And they want us to find the length of the slide. So the length of our slide is right here. Really wish I could draw better. It's a gross slide. But that's all right. It'll work for us. So now we have 53 degrees, 12 feet high. Length of the slide is x. All right. Which trig ratio am I going to use for this one? Sine, cosine, tangent. So I know we have 53 degrees. I know the length of this side. All right, that side's opposite of that 53 degrees. So the trig ratio that is opposite and the hypotenuse is, that's right, sine. So we're going to use sine 53 degrees equals the opposite over the hypotenuse. And now it is back to an algebra problem. Let's get x by itself on top, so out of the denominator. These x's cancel out. We have x times sine of 53 degrees equals 12. These cancel out. Now we're just left with our x by itself, which is what we want. And we have x equals 12 divided by the sine of 53 degrees. Perfect. Now we have our calculators one more time. So we type in 12 divided by sine of 53 degrees. We get x equals 15.0256, and that keeps going. So this is a length problem. We're going to round it to the nearest tenth. That should work. So we look at our 10 spot, and the number in the hundreds position is going to tell us what this is going to be. It's a 2. All right. So we have it. X is about 15 feet. That's really fun. I like these sine and cosine ones. These trig ratios are going to be really helpful as you continue to keep moving on in math. You're going to be using this in trig, calculus, all of them. So it's good that we're introducing it now and learning this stuff. You're going to have a lot more fun with it. All right, so that was section 9.5. The next one we're going to be covering is 9.6, and that's going to be solving right triangles. And that video will be on Thursday. So again, if you have any questions, feel free to email Ms. Kramer or leave a comment at the end of this video, and we'll get back to you, and hopefully we can clarify any questions you have. All right, thanks for watching, guys.